Okay, welcome back to the channel, everyone. Today we're going to be looking at integration by trigonometric substitution. Now, the main objective here is to look at how to integrate algebraic integrals by conversion to trigonometric integrals. So we're going to look at how we can take an integral that has algebraic expressions that we might not normally have a method to integrate it by, and we're going to convert it to a trigonometric integral and attempt to solve it. Now, when it comes to using trigonometric substitution, there are three main expressions that we look for. X squared plus a squared, x squared minus a squared, and a squared minus x squared. So we look for integrals that have these expressions, and with these expressions, we have a specific substitution. For x squared plus a squared, we use the substitution letting x equal a times the tangent of theta. For x squared minus a squared, x will be a times the secant of theta. And for a squared minus x squared, x is equal to a times the sine of theta. So let's take a look at an example. For this example, we'll look at the integral of the square root of 9 minus x squared over x squared dx. So our first step is going to be to choose the appropriate substitution. Now, since we are changing the variables from an integral in terms of x to an integral in terms of theta, we'll need expressions for both x and dx. So here, in the radical, we see that we have 9 minus x squared. So that's the expression a squared minus x squared. Now, in this case, a is going to be equal to 3, and therefore, we would use the substitution x equals a times the sine of theta. In this case, x equals 3 times the sine of theta. Now, with x being 3 times the sine of theta, dx will be 3 times the cosine of theta d theta, since cosine is the derivative of the sine function. All right, so now if we perform the substitutions, we'll clear off the board and do the work here. Once we choose this appropriate substitution, we want to convert the integral to trigonometric form. Now, if we do this here, 9 minus x squared converts to 9 minus 3 times sine of theta quantity squared over x squared, or 3 times the sine of theta squared. Dx becomes 3 times the cosine of theta d theta. So we've done all of the substitution. So we have this equation in trigonometric form. Now, once we do the conversion, we're going to use trig identities and simplification to rewrite this integral in the simplest form possible. So if we square out 3 times the sine of theta, we get 9 minus 9 times the sine squared of theta over 9 sine squared theta times 3 cosine theta d theta. We can factor out the 9 in the numerator to get the square root of 9 times the quantity 1 minus sine squared theta over 9 times sine squared theta times 3 cosine theta d theta. Now, the quantity 1 minus sine squared theta by the Pythagorean identity is equal to cosine squared theta. So that gives us the square root of 9 cosine squared theta over 9 sine squared theta times 3 cosine theta d theta. Then taking the square root, that gives us 3 times the cosine of theta over 9 sine squared theta times 3 cosine theta d theta. Now the 3 cosine thetas we can multiply together to get 9 cosine squared theta over 9 sine squared theta. After canceling out the common factor of 9, cosine over sine is equal to cotangent, and so after simplifying this, we just have the integral of cotangent squared of theta d theta. What you'll find in most of these cases is that by using this substitution, you'll have a fair amount of simplification, which typically will bring you to a simple, relatively speaking, trigonometric integral. So now we just have to contend with integrating cotangent squared of theta. So our third step will be to use standard methods for evaluating trigonometric integrals, which you would have learned earlier. Now for cosine squared theta d theta, we can use the identity, another Pythagorean identity, cosecant squared theta minus 1. Since cotangent squared theta plus 1 is equal to cosecant squared, using that identity, we can rewrite cotangent squared of theta as cosecant squared theta minus 1. And then from here, we can easily integrate term by term to get negative cotangent of theta minus theta plus c. Now, good news, bad news. The good news is that we've done the integration. Bad news is that we're not done, because remember, our original integral was in terms of x, not theta. So our last step will be now to convert this back to the original variable. All right, so now how do we do that? Well, remember our original substitution was x equals 3 times the sine of theta. Now, doing a little math here, this implies that the sine of theta is equal to x over 3, which if we solve for theta, that would give us theta equals the inverse sine of x over 3. So our expression for the theta is taken care of here. That part will be the inverse sine of x over 3. Now, what about the cotangent of theta? Well, for that, we'll need to dig a little bit deeper. Now, going back to our identity, or going back to the fact that the sine is theta, the sine of theta is equal to x over 3, by definition, the right triangle definition of the sine function, the sine is the opposite over the hypotenuse. So x over 3 would be opposite over hypotenuse. So that means that we can, if we were to construct a right triangle with the angle theta as shown, the opposite side would be x, and we can draw the hypotenuse as having a length of 3. So then using the Pythagorean theorem, that means that the missing side, the adjacent side, would be the square root of 9 minus x squared. So you can check that by using the Pythagorean theorem. Now that we have all three sides of this triangle, we can evaluate the cotangent of theta. The cotangent of theta is the adjacent side over the opposite side, which for this triangle would be the square root of 9 minus x squared over x. And so that will be the expression that we use for cotangent. And so therefore, our answer for the original integral will therefore be negative square root of 9 minus x squared over x minus the inverse sine of x over 3 plus c. So thank you very much for watching this video. I hope to have a couple of more examples available on my channel real soon, but this should give you a good start on how to begin working with the trigonometric substitution to solve these types of integrals. You have a good day.